Hi, myself Gopal. Today I am going to discuss about some numerical on simple harmonic motion, liquid in a U-shaped tube which executing simple harmonic motion. So you can give your valuable feedback at godphysics6@gmail.com. Now the question is here: calculate the time period of the liquid column of height L in a U-tube if it is depressed in one arm by x. Rho is the density of the liquid and A is the cross-sectional area of each arm of the tube, and corresponding diagram is given here. It is clearly visible in my video. So from this diagram, what we are going to find out, actually we have to find out the time period of oscillation of this liquid column. To solve this numerical, first of all you have to understand this diagram very clearly, because you have to know what are the changes that you will get at the time of execution of simple harmonic motion by that liquid in a U-shaped tube. It was clearly visible in my diagram in right hand side. I will describe this in details. You see the diagram. In left hand side it was shown that before application of any external force in the left arm of the U-shaped tube, the height of the liquid column is L. A is the cross-sectional area, rho is the density. So when you apply a force, small amount of force on the left arm of the liquid, it will depress of amount x. So the same amount x it will raise in the right arm. So what will be the total displacement of the liquid? So you see in the right hand side picture, left hand side arm and right hand side arm, the total difference is 2x. So the liquid is displaced of amount 2x. So by this change of height amount 2x of that liquid, the restoring force is generated. That restoring force is coming to act by this change of height 2x of amount of the liquid. So we can write the restoring force equals to the weight of that amount of displaced liquid. Now I will show you how you will calculate all of these things. So what is the mass of that displaced liquid? M dash equals to 2x. As the height change is 2x, so 2x into A cross-sectional area into density. So volume into density will give you the mass of the displaced liquid. So restoring force F equals to minus of M dash of G. So we substitute the value of M dash here from first equation. So we will get F equals to minus of 2A rho into G into X. So from there we can write F equals to minus K into X, where K is the constant, restoring force constant, where the value of K is 2A rho into G. Now we can write the equation of motion of the liquid is M d2x dt2 equals to minus of kx. In place of F we replace the value of force. F is M d2x dt2. So rearranging we get d2x dt2 plus k by m of x equals to 0. So d2x dt2 plus omega square x equals to 0. So here we consider another constant omega square, which is actually natural frequency, angular frequency of oscillation. So omega square is k by m, where k is the restoring force constant and m is the mass of the whole liquid. So now if we substitute the value of k and m from the previous equation, we will get omega square equals to g by L. So omega equals to under root g by L. So the angular frequency of oscillation, omega equals to under root g by L, where g is the acceleration due to gravity and L is the height of the liquid column. So from there, as we know, omega equals to 2 pi by t, where t is the time period of oscillation. So we can easily calculate our last equation, last expression of t, time period of oscillation. So t equals to 2 pi by omega, so 2 pi under root L by G. You can see here, the last expression will give you the expression of time period. So our problem is solved, and hope it is well explained. Thank you.